Swayam Prabha. Digital India. Educated India.
Lecture title is Introduction to Positive Displacement Hydrostatic Units. Hydrostatic units means hydraulic pumps and motors. Positive displacement machines are those machines which are having a fixed amount of volume transfer from flow input side to output side in each revolution or a cycle of linear motion irrespective of their speed. This means that whatever will be the geometric displacement, the same amount will be transferred from input side to the output side, let it be a rotary machines or a linear actuator. This is, of course, there is no leakage, we are considering there is no leakage. This is possible when a geometrically formed closed space chamber expands and contracts due to input motion of a component which takes part in constituting the formed closed space. For an example, let us consider a cylindrical piston within a one enclosed cylinder system, say tube well. When the piston moves, the geometrically cylindrical volume expands or contracts. We know this. It is called positive displacement reciprocating pump. With a proper valve arrangement and pipe conduit connection at blocked end of the cylinder, it is possible to take in fluid to the cylinder during expansion, which is suction mode, and the same fluid can be delivered in contraction or compression mode. Ideally, the amount, that is volume of fluid at incompressible phase transferred in each cycle is exactly equal to the volume at extreme expansion mode if there is no leakage. This volume is called swept volume. Now, here I would like to mention, contrary to this, if we consider hydrokinetic machines, which I have already discussed, say for example, centrifugal pump, there is physical connection between the input and output and the medium is being pumped. Say for example, a centrifugal pump is pumping water. You will find the water coming in suction side and being discharged, they have physical connection. Only we are adding kinetic energy to the fluid to generate the pressure at output side. Okay. But in case of positive displacement machines, the volume is taken in, then it is cut off. The whole volume is now pushed out in the output side, and usually you will find there is no suction head for positive displacement pump. However, depending on the machines, it may have low suction head. The pressure at outlet depends on the pressure head at that side due to the load which it is handling. It has no relation to the kinematic of the pistons. This means that if there is no pressure or it is not transmitting any load, only the pumping the volume, you may find there is no pressure on the oil, except it has to overcome some resistance. So, there will be some pressure. So, pressure is experienced. If I consider a pump, it is not pumping the pressure, it is pumping the fluid and pressure is being experienced. Now, one thing I would like to mention that we are talking about mostly in this lecture, incompressible fluid, that is mostly the hydraulic units. Now, only all the components must be, in case of as it is not pumping the pressure, pressure is being experienced at the outlet. So, we should have one able to withstand at that pressure, the component should withstand at that pressure, it should be able to take the loads, and the energy source must be applied to supply the energy to move the pistons. This means that if there is a pressure in the outside, if it then the energy must be sufficient to generate that much pressure. Okay. In such energy transfer, there is no hydrodynamic or hydrokinetic effect. That is why such a pump is called hydrostatic pump. In fact, we should call hydrostatic unit. It might be pump or it might be motor. The machine with reverse process, a linear actuator, lifting jack, is called a positive displacement reciprocating motor. We can have either linear or rotary. There is also another term is used which is called rotating. In one case, rotary means the position of the piston and cylinder fixed, only when it is the piston and it is some cam is rotating, these pistons are being actuated. But there is also a rotary pistons where the whole piston units itself is rotating. We will come to that later. Obviously, it is also a hydrostatic unit, that means linear actuator which is reciprocating motors, the hydraulic jack, it is, we should call it hydrostatic unit, we should specifically call it, it is a linear motor, linear actuator. For transforming more energy in a compact space, rotary units have evolved from the basic concept of reciprocating units. This means that say tube well, they only one cylinder is there, so it is reciprocating. Now, if we put few cylinder together and we actuate it with the help of cam with a phase, time phase, then we have to mix up, of course, the mix up the output, then we can develop a rotary machines. In fact, the rotary machines are like that. They are of various types as discussed in the next sections. As from the construction point of view, a pump and a motor from a particular variety look alike only with a minor difference in valve systems. It is very difficult to identify whether it is a motor or pump. In case of pump, we rotate the shaft and oil is taken in suction stage and it is delivered at compression stage. In case of motor, it is reversed. the high pressure oil is pumped in and then output is taken through the shaft. Otherwise, there is very difficult to understand which is pump or motor. It is indicated there. From there we can consider this is pump and this is motor. If we think of these components there is a valve. That valve, if we change the valve, the same unit again can be used as a motor. Even with specially designed valve, if we design the valve specially, a unit can be used both as a pump and a motor. When we learned about the symbols, there is a symbols that a unit which is used as a pump and motor, but we should keep in mind, if we design the valve to act both as a pump and motor, definitely we have to sacrifice some finer activities of the valve. In that way you will find normally such pumps or motors having a lower efficiency, but still it can be used. Such machines together are often generically called as hydrostatic unit. This term is many people, they are not much accustomed with that. Suppose even if within the mechanical engineers, if you say that this is an hydrostatic unit, these people will always, they will ask whether it is a pump or motor. They will never accept that it is a hydrostatic unit. Hydrostatic unit means this can be used as pump and motor, just changing the valve. But if you think of the centrifugal pump, of course that can be used as a turbine, but it is difficult. It is difficult, you have to change so many things there. Usually positive displacement pumps have poor suction head, which I have mentioned. We do not need even suction head in many cases. Usually the purpose for which we use the hydrostatic unit, we can put the pump even submerged inside the oil. However, the small suction head means in terms of the height, maybe 1 meter suction head may not be problem. Even for very good performance of hydrostatic units, sometimes a charge pump is used. We will come later on the hydrostatic systems when we learn about the hydrostatic system. Now, it is to be noted that such units, particularly the oil hydraulic units, have higher power output to unit weight. This I have explained, but still specifically I would like to mention that very high power output to unit weight, or you can say that moment of inertia to torque output. Torque output divided by moment of inertia, that ratio is high in comparison to the other systems such as electrical, water hydraulics, IC engine, etc. In electrical machines which are competitively comparable to oil hydraulic machines, flux density has a limiting value in a core size. That means, the motor core, which is, if we measure the flux density comparing with its weight, we will find it is have some saturations. We cannot make it very small to have very high flux density. So, that is why we cannot reduce this electrical motor size, and I have already perhaps told you, but still I would like to mention. Say for example, if we consider a 5 kilowatt electric motor, maybe it will be around 300 meter length and diameter maybe 250 millimeter. Whereas, if I think of 5 kilowatt an oil hydraulic motor, size will be maybe only 150 millimeter length and diameter about 80 millimeter. In oil hydraulic machines, more pressure density can be applied to its components, having much less weight than the electrical components. This is the advantage, that is, the fluid inside, it is generating pressure, equal pressure in all directions. So, load is distributed on the body, which is usually ferrous components, and if the load is distributed in that way, it can take much more load, more stress. So, that is why we can go for small size. In hydrokinetic machine, centrifugal pump, torque converter, fluid coupling, etc., the rotor gives a velocity to the fluid inside it, and a negative pressure or suction head is created at the inlet. I have explained. So, this is the difference there. In case of positive displacement pumps, the entrapped volume is pushed out at high pressure, which has no physical connections already, which I have already told you, with the inlet fluid. Therefore, no suction head or much lower suction head is created at the inlet. There is actually, we can specially arrange the machine to create the suction head, but it is of no meaning, it is not required. Various principles have been adopted to construct rotary hydrostatic units, pumps and motors. We shall in this lecture we shall discuss about the rotary pumps and motors, and we will see, we will look into that. There are various types of such motors and units. Most commonly used hydrostatic units are, one is the gear type, then vane type and cylindrical reciprocating type. These three are most common, and these are rotary machines, usually not rotating machines. They possess different leakage characteristics, valve system and other features. Some of them can be made of variable displacement. Cost differ with the variation in performance. However, depending on applications, they are selected considering the various optimization characteristics. You understand this, because if we would like to optimize some sizes, say for example, gear pump will have more leakages, we cannot optimize that leakage characteristics. In comparison to that, best will be the cylindrical reciprocating type, whereas vane type will be in between that. From application point of view, they are categorized as follows. Gear type, normally for low pressure 0.7 megapascal to 18 megapascal. Now, this 0.7, that is, we would say that we do not normally use the hydrostatic units for such low pressures, but it can perform at such low pressure also. Now, next one is the vane type, where 3.5 megapascal to 21 megapascal. Then why this 3.5? You may ask a question, will this work at 0.7 megapascal or even less? The answer is yes, obviously, but when we would like to have pressure range of this in between 3.5 to 21 megapascal, we would look for vane type. Now, in piston type, we have axial piston, which can be used up to 21 megapascal, and there are radial piston also, which can be used up to 70 megapascal. Now, I would say that these are all general purpose. We can have more pressure particularly axial pistons, we can go for higher pressures. Very carefully designed gear pump nowadays, it can give even 20, 21 megapascals or even more, and vane type also can give higher pressure. It is to be noted that gear type units cannot be made of variable displacement, whereas vane type we can make it variable displacement, and obviously piston type we can make axial piston and radial pistons both variable displacement. On the other hand, many kinematic varieties and features are possible with piston type units. Now, if we look into the maximum pressure capacity, then what we find, rotary abutment means it is a some sort of rotary, not exactly gear, and these are usually very low pressure. Next comes vane, next comes gear, but I think that vane also nowadays, this chart is not very up to date. Vane also can be made of high pressure, and next is straight axis, and I shall explain what is straight axis and what is bent axis and inline. Straight axis, that is a lower pressure, bent axis a little better, and inline means usually which is like a radial piston, it is called inline. They can go up to 10,000 psi, and this means that about 70 megapascals. In a reciprocating single piston cylinder with uniformly shaft crank rotation, the rate of output flow is sinusoidal. In multi-piston machines, flows are mixed. That has to be. Here I would like to mention that as flows are mixed, we call it DC, direct current. We can compare with it is a DC type machines. Whereas there is also possible we can make alternative flow hydraulic machines. However, this is not popular due to there is a valving problem, and it is not much beneficial if we do not want to separate the fluid, or I would say that for the same fluid it is not much benefited. That is why we do not go for AC. However, we need not consider at the present moment any alternating flow hydraulics. We should call all are direct DC flow machines. Now, we have here we have written that it is a sinusoidal effect, but it might have also higher harmonics. This is there. The pistons are equispaced with respect to shaft axis and its transverse plane, and the individual flow overlap each other with phase differences as shown in figure 5.72. In this figure, if you look into this, say this is one piston, okay. Next piston is this one, next one this one, next one like this. Depending on how many pistons, simply we can divide the 2 pi divided by the number of pistons, and then we can start each cycle from that angle, and we will get this sinusoidal curves. This curve ideally it is sinusoidal, but with higher, depending on kinematics, it may have some higher harmonics, but nature will be more or less same. The resultant flow ripple reduces with the increase in number of pistons. What is resultant flow ripple? this one is called resultant flow. As we are mixing the flow, for a single piston we are getting a flow like this. Suppose you are rotating in a gang shaft, a single pistons, you will find half cycle it is delivering the oil and half cycle it is suction, it is not delivering. But when you are mixing, for each piston, although it is half cycle delivery and half cycle suction, but for multiple pistons you will find that when one piston is in the suction mode, definitely another few pistons in the compression mode and they are delivering oil. So, ultimate flow ripple we will get like this. That means, if the shaft is rotating at a constant speed, we will find that flow is fluctuating. With the increase in number of pistons, that fluctuation reduces. So, we cannot go for very small number of pistons, and there is another factor, interesting factor, we will come to that now. The nature of flow rate pattern of a piston depends on its design feature and kinematic employed. Therefore, the nature of flow curve deviates from sinusoidal curve and possesses higher harmonics, which I have explained. However, there will be ripple in all cases, whatever may be the harmonics are there will be ripple. It is to be noted that in common hydrostatic pumps, pistons are single acting and only half the cycle remains connected to the delivery side. You should know this double acting. Say for example, in many cases you will find that, suppose if you take a linear actuator and it is had rod at the both side for equal volume displacement. Now, while it is going right side, then left side is suction, it is accepting oil or allowing oil to take in, whereas the right side it is delivering the oil, and when it is moving in the left side, it is vice versa. We can have a special valve in the suction side and we can have a special valve in the delivery sides, and in that case, although there is a single cylinder, but that we should call double acting, not single acting. But whatever rotary machines you will find with the pistons, normally they are single acting, not double acting, only one side. So, each piston is having half cycle delivery and half cycle suction. Only due to as they are being mixed, then when one is in suction mode, other in the delivery mode, and that is why there is a continuous delivery. Now, we can say this is a cycle, say maybe for the delivery side we have drawn this cycle. Okay. Now, referring to this figure, instantaneous delivery flow geometric displacement rate of a single piston is presented as a function of shaft rotational position assuming uniform input speed of the shaft. Okay. So, this is presented with respect to that uniform speed, omega is constant. Okay. If it is not constant, this nature will change, that is obvious. Okay. A polygon can be welded putting the phasor. What is phasor? You can, this is in electrical analysis these are used. You can consider a phase, that is say R is the arm, then amplitude you can calculate R of sin theta, and at any instant you can say that this is the amount of delivery. So, this is called phasor. Now, for all the pistons, if we draw their phasor together, we will get a polygon. Overall maximum flow Q max and minimum flow Q mean can be realized from the phasor diagram. It is like that. Say we have 5 pistons. So, what we can do, this phasor, say this is with respect to the shaft, this is the first piston position. The second piston obviously you will find it will be here, because this angle difference will be, say if this is 0 plus omega t, then this will be 0 plus 2 pi divided by 5, we have 5 pistons, plus omega t. So, in that way if we put all the phasor together, you will find this polygon, and this will be the, this height is the maximum height which will represent the maximum flow. This is analogous to the flow. That means, in the flow ripple the higher point can be find out this by this one, and the lowest point will be this one. That means, if I rotate this one on this line, then it will, this point will generate a curve, say small curve this one, then next this one will generate the other curve. So, in that way we will get a wavy curve which is the flow ripple, but this is again ideal. We are not considering any harmonics, higher harmonics, only on the basis of sinusoidal. However, this can be, we can formulate this one. Now, flow fluctuation for multiple pistons, number of pistons say n, are estimated using the formula simplified and approximated as below. It is simplified one. You will find that even if with this, if you calculate, then this formula, that q max minus q min by q max is not this one, there will be some other term which you can neglect, but you can arrive into this simplified equations neglecting the other parts, and 1 minus cos pi by 2 n is for odd number of n, and for even number of n it is 1 minus cos pi by n, where n is the number of pistons. Now, this can be plotted for different cylinders, multiple cylinders, and this we have presented here in this table. Now, if I consider 1 pistons, then q min is 0 in the flow ripple, that it has will be 0 definitely, okay. And so this will be 100%, 100% fluctuations. That means, if you consider the sinusoidal curve, it will be from the top to bottom at the 0 line. So, this is 100%, and if we look into this formula, this is quite interesting, that for 2 pistons also it is 100%. Now, when we use 3 pistons, remember those formula, just n is equal to 3, you will find this is 13.6, only 13% fluctuations. If you go for 4 cylinder, it is again increasing. This is, you can visualize like that. In case of odd number, it is like that, they are lagging after one another is in such a way. 3 pistons are in delivery when 2 in suction, say let us 5, or even if for a 3, 2 in delivery, 1 in suction, or vice versa. In case of 4 pistons, there is a situation 2 in delivery, 2 in suction. So, that is not advantageous. For 5 pistons, you see this is reduced to 4.9, about 5%, and for 6 you get again 13.4, which is, you find it is for 3 pistons. The same fluctuation we will have for the odd number 3 pistons and even number 3 into 2 6 pistons. Okay. That means, if you get any even number, you will find that if you divide by 2, you will have a odd number, the same fluctuation will be there. If you divide an even number get another even number, then again you have to divide. In that way you can find out, except if you divide 4 divided by 2, then 2 piston is not having the 27.3, it is having the 100% fluctuations. Otherwise you will say, for example, 8 is having 7.6, this if you divide it is 4, it is having 27.3. So, you will find that this is having different, but all in the higher side, whereas if you go for 10 pistons and 5 pistons, they are having same, because 10 divided by 2 is 5. Okay. Now, in that way, if we arrived into 11 pistons, you will find that it is only fluctuation is 1. So, next if we go for a 13 pistons, you will find this is less than 0.5. So, this means that if you can use the 13 pistons, we would say there is no fluctuation, and it is better to use the 13 pistons machines. Why 5? We should go for 13, but you should always remember, with the increase in number of pistons, the cost will increase. Valve porting will be problem, second problem. Thirdly, in terms of reliability, you would say that when they will start a little error, then the dynamics will increase in case of more number of pistons. After certain time, you will find all the pistons and cylinder are not of same size. Within the tolerance zone, they are different. Now, when they are worn out, if there is more number of pistons, dynamics will be increased. So, in that way, what I would say, you will normally find the multiple pistons, there are not less than 5 pistons, whereas not more than 13 pistons, not more than 13 pistons. However, 5, 7 and 9, these three are very common, 5, 7 or 9, mostly 7, as 7 is a very good number for the number of pistons, for which only 2.5% fluctuations, and considering the leakage, it is slightly in higher side. It is interesting to note that unit with even number of pistons has much higher ripple than the unit having lower but odd number of pistons. I would say that in interview normally it is asked, it is a question that why there normally you will find this odd number of pistons in hydraulic pumps and motors. Answer is here, but I would like to mention, in case of gear pump or vane pumps or vane motors, this is not followed. Usually vane and gear pump, they are having more than, easily it can be designed more than 13. So, maybe 20 teeth, that means there is a 20 pistons in case of gear pump, and there for the 20 pistons you will find that maybe 2%, 3%. So, not much difference. So, this is only or mostly for the cylindrical piston machines, which are used for very high pressures. Also for even pistons, the ripple is equal to that in unit with half the pistons if it is odd, not for the even. Say, as I told, 8 divided by 2 is not giving the same fluctuations. This can be realized from another figure. Now, here I have shown what we have done. Say, this is of 5 pistons, okay. This is another 5 pistons. Now, obviously, if I consider this of same phasor, definitely say this means that, say, I have drawn the 10 pistons phasors like this and 5 pistons. Now, as the length of this arm are same, this means that we have used same pistons and same stroke for constructing 10 members, 10 piston machines. Obviously, the for the same rotation the delivery will be double. Now, to make the delivery equal, we have to reduce the size up to half stroke, and but if you look into the nature, you see this is showing the 5 piston minimum flow, mixed flow minimum, this height, and maximum will be this one diagonally. So, when it will become the straight vertical, this line will become vertical, but in case of 10 also you are finding just double of that. In case of the minimum one, it is just double of that. That means, we are going to get same nature, only it is multiplied by 2, and if we divide by 2 for in case of 10 pistons stroke length, then it will give the same nature. Just with this phasor diagram we can realize this. Now, we are considering for the ripple, we are considering an example. Now, this is what we have shown, that is axial piston pump. How it works, we will come into detail later, but let me explain a little bit. This is called a barrel. Barrel means it is just a cylindrical body of thickness of this much, and then there are holes. How many holes? That depends on how many piston we are using. You can see here we have used 7 pistons. So, there are 7 equispaced holes on which the pistons are placed. Now, this plate is called swash plate. This can be made fixed, or this can be mixed variable angular displacement. That means, this alpha can be varied. In case of variable pump or motor, this can be varied. In case of fixed, this alpha we keep fixed. This is the tilting angle of the swash plate. Now, let us consider this piston, or say the top one here, this pistons. Now, this is while it is rotating like this, it is coming this side and again it is going up. So, that means, while let us consider from this side it is rotating a clockwise. So, this point is going beyond the screen and it is rotating like this. So, gradually this piston is coming out and the stroke is increasing. That means, total strokes can be taken from this point to this point. If I draw a straight line, this is the total stroke. So, one side it is a suction, another side it is a delivery. Now, in pump version, the barrel, what I have explained, this is written here. It is equispaced on a pitch circle, and this is a central housing shaft through this, while the piston ends slides on a stationary inclined plate. Now, there is an arrangement so that the piston is always touch this swash plate. It is written here, it will always touch the swash plate. As a result, the piston reciprocate, generating suction and compression volumes. Now, instantaneous volume of a piston can be written by, you see, pi d square by 4 is the area of this piston, one single pistons, okay, and then dP is their pitch circle diameter. dP tan alpha is the stroke length. Now, this stroke length we can, it is varying with the shaft rotations. What we have to do, that we have to this, if we imagine this height, then this is a sin theta. So, that is the displacement volume. Okay. You can just do this exercise of your own, you will find that this is the instantaneous position of this piston. So, if we plot this one, we will get the flow curve. So, that is why it is called, this is a sine curve, because this part is fixed for when alpha is fixed, and this is also a fixed part. Now, theta in degree in the position of a piston in clockwise directions we have considered. So, from 0 position this piston has rotated this much. So, we have multiplied with sin, we have taken sin theta. For this piston, how much we should take? Theta plus 2 pi divided by the number of pistons. So, this is written here. This means that for a piston, we would add the angle of rotation of the barrel along with the initial position of the piston from that axis. Okay. This is very simple. So, if we would like to plot this one, we have to add theta plus 2 pi by number of pistons. Now, this we have plotted here. Now, what we have considered? We have considered the blue one is the 7 piston. We have taken 7 pistons, and for 7 piston is this one. This is the fluctuation. So, we have used the same formula, or it might be the exact variation formula. This formula what we have developed, that we have used to plot this curve. Now, this we have not mentioned the unit, it might be meter cube or maybe inch cube, like that, depending on the size. So, even if this can be presented in dimensionless form. Now, for 9 piston, as you see, this ripple is being reduced, whereas in case of 8 pistons, this is increasing. Now, if I consider this angle, this is around how much? This is 18 degree, because 360 divided by 9, no sorry, 20 degree, it will be 180 by, because half cycle 180 degree pi divided by 9. So, this is 20 degree. Okay. Now, in case of 7 pistons, this is 180 divided by 7, how much? It is about 2 and 40, 25.5, I think, like that. So, you can see this is the angle. In case of 8 pistons, so it is how much? (180) divided by 8, (22.5). But you can see this curve is like this, because they are overlapping. So, because 2 pistons, 4 pistons suction, 4 pistons. So, you will get this type of cycle for 8 pistons in one. So, if you plot that equations, you have to you can do such exercise, because in usually this is a questions that what will be the pistons showing this Swayam angle. We do not shown here the offset of this Swayam. It is pivoted on the axis of the shaft. In many cases, or not many cases, in some special design, this is also a offset. Once we put that offset, we will find that another term will come. So, this curve will be slightly different from this sinusoidal curve. Okay. So, in that way we have what we have understood, that by the phasor analysis we can find out the in general form what will be the flow ripple in rotary piston pumps. And for that I would say that the references are the same hydrostatic transmission system by Korn. We can follow this, and particularly if we would like to know more about the phasor diagram, because this is I have not seen anywhere except in that books. This is by Professor Jean Thoma, who is also, I would like to say, he was one of the pioneer who used bond graphs in fluid power. He is a man from Switzerland. Fortunately, he came here. He came to IIT Kanpur, and I have met him. And in his book, you will find that phasor analysis, but the formulation part is not given. You can try of your own. You won't arrived into that equations. Only thing you will get some equation close to that. You have to neglect the part which is having less contributions. Now, another I suggest that you should read the papers on this pump motor design by Mandring. There are many other people, but Mandring, he in recent times, in last 10 years, he has published many papers. So, if you particularly if you would like to know more about the inline piston pumps which I have shown in this figure, you can follow, you can website, you can just click on the Mandring's name, you will find that this paper is available there. This particular the paper which I have mentioned, this is still in online. If you click his name, you will find a list of papers, and then if you click on this paper, you will get this paper. You can read it. Thank you.